Okay, so let's continue. We start from the uh, the example, just before the example. So now I'm sharing again the screen. So this was what we discussed, and now I changed I did some corrections on the equations to just make sure that everything is clear. So the polynomial function that we are considering, we have. Oh, sorry, the recording is finished. We have w0, which would have x of 0 times x to the 0, which is always 1. So that's why it's w0 all the time. And w1 of x to the power 1. So we don't need to put power 1 here because it's, it's understood. And then w2 x to the power 2. So that's where the polynomial is always strictly stated there. But I want to put these numbers so that it will be clear to all of you. So the polynomial function is like this. It is a pair of a weight multiplied by the input variable x. Okay, depending on what degree, what order the variable is. Okay, that's the polynomial equation. So now the error, we try to minimize this error, and to minimize this error, we take the derivative of the error with respect to each of the weight. That is the gradient of the error. That is partial of the error with respect to partial of w's of 0, how the error changes when w's of 0 is changed, and so on. The weight, how the error changed with respect to w sub 1, w sub 1 changed, error changed with respect to w sub 2 until the error changed with respect to the change of w sub m. Okay, that's the point. So now this approach is called the greedy approach, the greedy search method, which is otherwise, of course, known as the gradient descent method. I want to use this because it's easy for students, especially for at the introductory level, for you to just go with the computation in trying to numerically compute the optimal value of the weights. Okay, so we did already the computation for you. So what we need to do is that, for example, the term of partial of E of the error with respect to the partial of WI, it will be this term here. So the polynomial approximation, the polynomial value of whatever your weights is now minus the target value multiplied by the input variable x at the nth data set. So now, of course, all these things are just abstract information until we do the example. Okay. So now let's go for an example. Okay. So we will compare analytical and numerical method. Analytical, I call analytical method, is the approach that you normally use during your math course, the engineering math course. And then numerical is that how we are going to do it as a machine learning approach of computation. Excuse me. Of course, analytical is good because it's a one step, it's always definite. There's a specific answer to every problem. But I mean, not all, but most of the time. But the bad side of it is that as the data becomes much more complicated, the computation becomes much higher, the computational expense. And then in this case here, the numerical approach or the machine learning approach will be a much better approach to do. That's why a lot of many technologies now are based on machine learning because of this ability of machine learning to come out with a solution, although an approximated solution, not an exact solution, but a good approximation of the problem at hand. Okay, so now let's consider this. So an example again of a data that is x, this input, and then I mean t as the target. So it's not time. So t is the target and x is the input. So I represents the data, the index of the data set. So this is your first data set. Okay, xi, x1 is 0 and t1 is 20. So the target at x is equal to 0, the target is 20. So at x2.1, the target 2 is 30, and so on. Okay, we have 1, 2, 3, 4, 5, 6. That means in the sixth set, you have x6, x sub 6 is equal to 0.5, and the target is 20. So if you plot it, it will look like, so you have an x here, you have an x variable that is equally distributed, 0.1 from 0 to 0.1, 0.1, okay, 0.2, okay, sorry, take it right, yeah, 3, 4, and 5, yeah, 0.3, 0.4, 0.5. So an equal distribution of the x value. And then we have our target value of a t, okay, that is now, say, this is 10, 20, I don't know if I can have it, 10, 20, 30, 40, 50, 60, 70, just nice. Okay, so 10, 20, 30, 40. So we can say that probably we don't know exactly what is the physical meaning of this one. We can say that, for example, is a temperature gradient. That's easiest way to say. So that means that, for example, there's a room, yeah? We can say that this is the X, I mean, the slice of a room. The slice of a room in the volume of the room, I take a slice, and then in that slice, from this side to that side, let's say, for example, the room is 0.5, what is this, 0.5 of a meter, that's very small, but let's say 0.5 of what, it should be 5 meters, yeah, 0.5 of what, 0.5 of 10 meters, okay, so that's 5 meters. So let's say that this is a room, and then this is at the point, we take the measurement of the temperature. So let's say at okay, at 0, your temperature is at 20. So here you have 20. So at 0.1, your temperature is 30. So that's the data. At 0.2, the temperature is 50. Okay. At 0.3, at the slice, the distance 0.3, the temperature is 60. It keeps on increasing. And at 0.4, it's 70. Okay. And suddenly at 0.5, it goes to again 20. Okay. So let's say, yeah, there's a room, a slice of the room, and that's the room temperature. Now, we want to connect, we want to know what is the best approximation of that function that will connect somehow. I don't know what's the connection. Maybe it will be something like this, like that. Yeah, maybe. Yeah, maybe that's a good approximation of the function. So what is that function? That's the question that we are trying to address here. Okay, I am recording, right? Okay. So now let's continue. We clear all that, and then let's continue to the next slide. So if we use analytical method, okay, this one has been done by you in the previous engineering class. So we just have to write all the equations. Okay. So 20. Okay. For example, 20, the first set, our target value is 20, is equal to W sub 0 times X sub 0, I mean X to the power 1. Okay, that's 0. W1 times X1, that's 0. Okay, and then W2 of, we will just writing this one. W2, which is W2, we don't know, W2 and Xn squared. So as you can see, our target is 20 and the X is here, okay, multiplied by the weights. Okay, and the next set, our target is 30 is equal to, again, 1. This column here is 1 all the time because we multiply W sub 0 with 1. This is 1 all the time. That's 1. And then here is xn, or xn, this one, I mean xi, our xi is 0.1. So, and then here is 0.1 squared, the same. So now the target is 50. So 1 again, 0.2, because this is 0.2, again, 0.2 squared. Okay. And then 60, 0.3, 1, 0.3, 0.3 squared, and so on. Okay. So in this case, we have a table of x. So this table can be our big X table. And this vector is our t vector. Okay. So our unknown weights is of course this W. Yeah. So we want to know what is this W that will give an approximation, a good approximation of this function, the second order function. It's easy doing analytically. Yeah. All you need to do is go to MATLAB and compute, solve this problem. So W is equal to the inverse of X multiplied by the target T. So in this case here, you will immediately get a function, a value for your W. Okay. That's the analytical method. Very fast. Okay. Again, if the data is very large, it will be very difficult to come out with a solution. Okay. So now of course, it depends on what you want. If you want to do like analytical method all the time, it's up to you. But for now, in this class, we're giving you an alternative solution on how to deal with this kind of problem. Of course, this problem can be done analytically. We'll solve it numerically and see what's the result. Okay. So we don't want to show, normally I don't really do the answers. Answers are not more important to me. More importantly is for you to show me the solution. Yeah. If you give me the full solution with no answer, I can still mark you almost 90%. Okay. Or 99%. So let's continue. Again, we are given this data and we want to find the values of W given that our approximation of the polynomial is a second order polynomial. Okay, so the first step is we initialize the values of W. Okay, so normally I don't tell students, especially in the lab, it's up to you to initialize. I don't give you an initial value for you to go around and see how things change if your initial value is different. So if you choose your initial value correctly, you will be as good to go to the optimal value at a few steps. But sometimes, you know, the optimization valley can be very rugged to the point that you can get stuck somewhere. Okay, we'll discuss that one some other time. But the thing is, there's a valley and hills where you're going through and to look for, computationally, to look for the tip, or it depends if it's maximization or minimization. So in this case, minimization error. So it means minimization is going towards the valley of the error. Okay, so there will be some hills everywhere, and then you can get stuck on those hills. Okay, in a small valley. Okay, not towards the global to the global minimum, to the global minimum of that value. You will be somewhere stuck with. You thought you're already there, you found the solution, but no, you're just in a small valley where the large valley is down there. Okay. Anyway, we can discuss this some other time, but. Again, we say that we need to compute the gradient of the error. So the gradient of the error, we have already seen, we have already derived this, which is the polynomial function approximation, which you have here. Here is your polynomial function, and you already have your W's initialized in this step. Okay, so this value, that value is known, and then you have your X values. Your X values are your data. So this is already known. Okay. And your Tn, this is already known. Those are your target values. And your Xn to the power of your W weights. Okay, the power of the W is equal to the subscript of your weights, and so this is also known. So everything is known. So all we need to do is compute what is the error term corresponding to the change for each component of the weights. That is partial of W0, partial of W0, partial of W1, partial of W2. Okay. So now, once we know this error, we go to the next approximated value of W. So that's the steps for numerically computing solutions. It's always an iterative computation, so that you can just initialize to some value. Hopefully, you will reach the global optimum value of your weights W. So now, whatever value that you do, okay, you will correct it with the learning step multiplied by the gradient of the error. Okay, and then now you solve for the next W. Okay. So after you get that new W, you repeat the steps until the error is minimized. How do you know that the error is minimized? You can check if this error term goes approximately to some value that you want to set. Yeah. So in your program, for example, you set a step here. This is a while loop, a do while loop, while, for example, error is less than, while error is greater than zero point 0.1, for example, and then you continue solving, yeah, until you're satisfied that the error less than 0 0.1, and then you quit. You say that you have found a good approximation of your W's. Okay. But in the class, what we will do is I will set the number of iterations, say 3 iterations. Then that's what that's up to the required number of computations that you will do. Okay. So again, the same. I'm just showing here how you're going to compute. So looking at the same data, we initialize the W. We say we initialize W to be 1. All of them to be 1. It doesn't matter, just for the sake of discussion. Initialize them to be 1 and compute the gradient of the error. So compute the gradient of the error. Again, this is partial of W, partial of the error with respect to W sub 0. Okay. So if you go here, this is your this is the computation, and this is your polynomial. That's the polynomial. So here, your polynomial minus the target value multiplied by the x. So we can see here your polynomial minus the target value, and this whole thing multiplied by your xn, that is the x, your n goes from 1 to big N, that is the data set. Your n, this is your data, xn, then to the power of the subscript of your W. In this case, W sub 0, W1, W2. Okay. So in this case here, for W sub 0, your x value is to the power 0. Okay. All of these are your x values as the data is given. And so x1 to the 0, x.2 to the 0, x.3 to the 0, because the power here is always the same as the subscript. Okay. So to the 0, these values to the 0, that means all these values are 1. Okay. So all those values are 1. And then what matters here are the things inside. So this is because our weights are set to be 1. So here, all our weights are 1. And so what happens here is 1 multiplied by the input value, okay? X, according to the I here, according to the data, to the power of 0, 1, 2, okay? So here, the weights, W1, W2, and W3 are all 1. So that's all 1. So this is X1 to the power, hey, this is not squared. It should be 0. Okay, sorry. I have to change this one again. This should be 0 because according, let me do the, or maybe this should be 0, all be 0, because according to the polynomial, this should be 0. Okay, the same thing as here, 0, 0. Sorry, I thought I did well today because I rewrite everything nicely. Okay, so that's 0. Okay, so now the exponents here are 1 and the exponents are 2 because that's the polynomial. Yeah, and so that's W1, W2, W3, W1, W2, W3 multiplied by the data. Your data is X1 data. So now is X1 is 0, so 0, 0, 0. So there's always 0 and to power 1, power 2. And next, X2 is 0.1, 0.1, 0.1, 0.1, 0 to the power 1 to the power 2. Next, 0.2, and so on, 0.3, 0.4, and 0.5. Then minus the target value, which is your target value here. Okay, the first target value for data set 1, data set 2, and so on. Okay, so you compute this, the polynomial minus the target value multiplied by the x of the data set to the power of the exponent to the power of the subscript of your W. In this case, this is 0. So in this case here, as your W change, inside it doesn't change. Okay, only this part change. as you can see, all this part here remains the same. If you make it as a matrix, you multiply this vector here, okay? And it will be, here is the same vector, but the only difference is that the exponent now is 1 because this is with respect to W1. Okay? Okay? So the terms are easily, you can substitute them easily, but then, you know, computationally it can be tedious because, of course, we are not supposed to do this manually. Okay? We're supposed to do this with a computer. But because of the class, we need to do it manually so that you will have a feel of what is going on in the computer. Yeah, you need to have the pain of computation. You need to understand the pain of computation so that you gain a good understanding. Okay, so yeah, it will be come to class with good hands during tests and examinations. Come to class with hands that are well rested, so that, you know, you'll have many computations, you know, as during tests. So now this is the first two terms, error term with respect to the change of the error with respect to change of W sub 0, change of the error with change of W sub 1, and we go back, go forward, sorry, to, again, this one is 0, to the third term, error term with respect to the change of W2, yeah? So again, this one is squared already. The terms remain the same. The terms inside remain the same. So when we update your W, so now you have W0, W1, W2 is equal to W0, W1, W2 minus your eta times what is computed in the previous computations. This, and that, those three terms, and there. Now we have new value of W, okay? Then you repeat the process. As you have new W's now, so here, this one will change, okay? This one will change, okay? Your previous computations will remain the same. Now only the W's will change, okay? All the rest of them your data remains the same. So now only the W's, this column here, that column there, and that column changes. Everything the same thing, that column, only this column and that column. The rest of them are the same, and the same thing, this column. That's why, you know, it's really for programming, because you just need to change the W and just repeat the function, and then that's it. You have your this value here, and then you can easily derive the next step. Okay, so you repeat the process from 2 to 3, from these two, this is the gradient, to 3, until the error is minimized. Okay, that's it, finish. So there are two methods that we just presented. Okay, let's just recap so that it will be clear to you. There are two methods. Given this data, two methods that we can compute. Yeah, so you need to find a good approximation of the polynomial function to the second order. Okay, given this data. Okay, so what you can do analytical method. Finish. If you have a computer, you can find it. No problem. Yeah, but the only problem is that if the data is very large, you cannot do this, or 1,000. You know, 1,000 by 1,000. You know, 1,000 by 1,000 matrix. Maybe it will take a very long time. Or 10,000 by 10,000 matrix. It will take a long time to compute. And then here, you can just do a search in the space using gradient descent method. Of course, gradient descent is not very recommended if there are many other methods there, but this is just for fast understanding. There are many methods of going through the optimization space, okay? So yeah, we can discuss those, many other techniques, but in this, as you grow in the in the numerical methods, computation, and machine learning methods, you will find that there are many other steps or algorithms. Basically, it's the algorithm, the method of computation for the error, on how you deal with the error term, are considered to be the steps of the algorithm, the different algorithms in machine learning. Okay, so here you have a gradient descent method. So now we use this method by just randomly initializing W. We know that this is the gradient of the error, and then now this is the most important step in updating your weights. Okay, so that's it. You update your weight, and accordingly you check your error, and you see the error has minimized. It will eventually be minimized. We don't know whether it will be eventually, normally it will go to a minimum value much better. I mean, your error go to a better approximation, much better than the initial value of your W. But the question is this the best W? Maybe there may be a better W if you try to use different initial values. Okay, but for me, I will prefer that if you go the examination, I will see that I will check. I won't give you initial values. Initialize your values. You don't copy from each other. If you have the same initial values, that means yeah, it gives me a red flag. Okay, so different initial values. You choose your initial values, and then that's it. I will check whether your final value is correct. I mean, the steps of the computation, of course, final value is correct, but final value doesn't really matter much to me. Okay, so that's it.
So,
Any questions?
so
Yes.
are there any specific tips or methodologies that we could apply in terms of picking out a good estimate for where to initialize our W?
No. Right now, no. We
There's no specific.
no specific.
Mm.
We just randomly initialize it. Of course, you can run in the computer program. You can run some simple steps and see how fast you converge like that. There's other techniques that you can use before you select a good pick randomly and then pick which one is a better initial value. Then you start from there. But for the sake of the class, yeah, it's for me to ensure that students don't copy, especially now that we are going online. So I normally do that. I mean, it's easy to check whether the final values. I mean, I'll just look at the steps and then the final value, not really that much weight on it. Okay.
And then you
So
also
1
mentioned
minute
that,
of computation. Yes.
yes, I was saying you also mentioned that there's other methods besides the gradient descent, and that the gradient descent is not really that good. And I understand that in this class we'll probably be focusing on gradient descent specifically, but for interest sakes, are there any other methods you'd say maybe are worth looking into in terms of minimizing the cost function?
Yeah, there are many methods. For example, radial basis function like that. Other functions that are done by many other algorithms. For example, neural network. Let's just it depends on what kind of computation you use. Neural network, you know, backpropagation method like that, and then radial basis function. So there are, and then support vector machine. There's also other functions that you use, not just gradient descent. But the gradient descent is popular because
Yeah.
it's easy. It's easy to compute and it's easy to use. And in most of the cases, it is good enough. But it is not good enough if you're really looking for, very serious, results. Most of the time, it's not good enough. You're looking for serious results. But for approximated results, it is good enough. So yeah, there are many computations out there that you can consider. But in the class, especially for, I mean, we're oh, 10 minutes more. We are going for different types of algorithms. For example, decision trees, we won't be using gradient descent method. Bayes rule, we won't be using gradient descent. So in this case of linear regression, we are using gradient descent because is the most logical computation to use.
Okay, no, thank you, sir.
Okay. Have you done gradient descent before? Any of you have done gradient descent before? Okay,
Well,
there's
personally, not like this, because like this is clearly engineering orientated. But yeah, I've come across it before. Still, the numerical method was just a bit more watered down, I think, when I came across it. Yeah.
okay. Yeah. the most of the case, this function, the decree, trying to look for the correction, the error correction for the weights, is the one where that spells out the. If you can see most machine learning techniques, it's just looking for the weights. Okay, like a support vector machine is a different equation, but the computation is just looking for weights. Yeah, neural network is a different equation, but the computation is looking for weights. Yeah, so all of these, most of the things are there looking for weights, and the way to compute the weights spells out, you know, the algorithm, the technique that they are using. So in most cases, whatever the technique is, I mean, whatever is the algorithm is, there is their own way of computing that in order to minimize the error. Okay.
All right, sir.
Mhm.
Thank you.
Anything else? I was wondering if Admire was not around, who will ask questions? Tom, can you ask a question? Our engineering guys are normally they can't express their feelings. That's what I was told. I mean, of course, we are good at doing, but we are not good in expressing our feelings. Okay, that's what my teacher used to tell me, and I think it's true. Okay. Anything else? Okay. What I want to do is actually I wanted to do an exercise so that an a surprise exercise today, so that those who attend will have an advantage. It's not easy to attend nowadays. That things are not, you know, things are unclear. But anyway, so I will give you an exercise just to emphasize on this topic that we have discussed as an assignment. I mean, as a lab exercise, a second lab exercise. Okay. So what you will do is you will do a numerical analytical method, then a numerical method, and then plot the results. Okay. Do it manually. I want you to do it manually first, and then you run. It's either MATLAB, I don't know what you're familiar with, MATLAB or Python or TensorFlow, whichever you want to prefer. So just show that, in a very simple term, I mean, this is a very simple exercise. This is just introductory. It's a simple exercise. You do manual computation, and then we do computation with the computer and see how things go and graph the results. Okay? Okay,
Oh,
I think it will be a fun semester. I look forward. Some of you have been my students before, and you know already my kind of questions that I want to ask. And some of you even have this class already before, so you will know that you really need to come to class with rested hands, so that during test it will be a very long computation. And I suggest that you don't. During examination or test time, please don't, there's no need to study. When you come to test time, you should just write like, very minimal thinking. You just out of practice. Okay? That's the way that you beat the time for the test or for the examination. Otherwise, if you come to test or examination and still studying, you won't have enough time. Okay? Especially in this class. The computation is not that tedious, it's not that difficult, but the computation is not that difficult, but it is very, very tedious. Okay? Because we are trying to do what a computer is supposed to do for us, just for your understanding. Okay, anyway, it's already time. And then otherwise, see you next time, next Friday. I still don't have a TA now for the lab. So I will do the lab exercise. I will send you a second lab exercise, but it will just accumulate the lab as the TA is around. So now, because TA is not there, we'll just make it as homework. Okay? The take home lab exercise, you do it whenever you want, but then the deadline will be just before the new lab session. Okay? Okay, we already have one lab session, one lab that is due next Thursday. And so the next lab will be due the next Thursday. Okay, otherwise, see you all again online on next Friday. Okay. Okay, if there are
Yes,
no
sir.
questions, please, those who want to, I will off the recording now. Those who want to check with attendance, you can remain so I can check the attendance. Thank you guys for coming.